Right, this video sums up the types of resonance. So there are several. There is the unshared pair of electrons, whether it be a negative charge or lone pair next to a pi bond. So say we have this amine next to an alkene. There is a lone pair on the nitrogen. That lone pair can shift to form a double bond and break this double bond to give you a resonance structure that is not necessarily most stable, but it can happen. Just show an example of a negative charge. So if we have something like this oxygen in this case with a negative charge, it can resonate, give the oxygen carbon double bond and a negative charge on the carbon adjacent to it, and do further resonance. Yes, we'll agree. Happy times. All right. There can also be an absence of electrons next to the double bond. So next to pi bond, double bond. See, they're pretty much interchangeable. So what does that look like? So we have some system like this. Oh, the carbon has a positive charge on it. Well, that means that the resonance is now going to be coming from the bond next to it to form a new double bond where the plus charge should be, which looks like this, but now the positive charge will have shifted. We can now resonate further. But notice how the charge is moving along in the opposite direction of the arrows, whilst with the negative charge forms the bonds that are becoming double bonds. So key point, direction of arrow, important, moves towards positive. Why is this? Well, because the arrow depicts the movement of electrons and there are no electrons in the absence of electrons, which is a positive charge. We can also have a single electron next to pi bond. What does that look like? So you have a radical such as this. Well, to depict the movement of the radical, we actually have to use a half-prong curly arrow. And this is the movement of single electrons, so that we end up getting a resonance structure where we have a double bond and a single electron at the end of the other previously pi bonded carbon. So let's just focus on that. The half prong curly arrow specifically denotes movement of single electron So what would be the difference? Well, I guess now is a good time to go over homolytic and heterolytic bond splitting as well. So homolytic bond splitting is where you have two atoms, let's call them X and X, bonded. Recall that this is X with two electrons in between them to form the bond. The bond splits equally with one electron moving one way and one electron moving the other to give you two radicals. Heterolytic bond splitting is when you would have both electrons moving to one end, such as this case where you would end up with X with a positive charge because all the electrons left that atom, and an X with a negative charge where the other atom gained both electrons. Notice how we use different arrows for homolytic splitting. These are the half prongs, and we have the regular heterolytic splitting where we end up with charges. Cool. Back to resonance. Double bonds between two atoms with different electronegativities can also resonate, but note that the electrons always move to the most electronegative atom. So the most common one that you are going to encounter is a carbon-oxygen double bond. So here's a ketone. If this was to resonate, the electrons must move to the oxygen to give you a carbon-oxygen single bond with a negative charge on the oxygen and a positive charge on the carbon with this heterolytic split. If we were to draw it going the other way, we would get a carbon with a negative charge and oxygen with a positive charge, but this is preposterous, impossible, cannot happen. Do not draw it. You will lose points in an exam. Finally, pretty much the most common use of resonance is with respect to rings. So rings and resonance, well, resonance becomes infinite. And we're not joking about that. That's why a ring structure such as this is so popular in organic, because when you have your electrons shifting, you usually tend to end up with something that looks pretty much exactly the same. And we can now do this infinity times, go back and forth and keep the same structure. But these are resonance structures. Just note that a cycle is infinite. Of course, further on, if we start looking at the other stuff we can do, if you have a ring with double bonds, so there are pi bonds, and we happen to have, say, an oxygen with a lone pair on it, well, two lone pairs. This lone pair can donate into the ring and cause a resonance structure. Like something like this. Now the resonance structure can move around further. No questions asked. Well, not too many questions asked. I will definitely ask questions in exams. Look forward to that. You will get something that looks like this. And we can then go back to our original. Notice how this was a lone pair donating into it, so a negative charge. The same can happen if we happen to have a positive charge, such as here's a ring, here's a nitrogen, we'll put a positive charge on it. Well, now this double bond can resonate, although a double bond is going to have to break to put a positive charge on the ring. And maintain the charges before. Notice that this was neutral, therefore this one must be neutral too.